Hello friends, in previous lecture we have studied Euler phi function. So for positive integer n greater than 1, Euler phi function phi of n is a number of positive integers less than n which are relative prime to n, and it is denoted by phi of n. Moreover, Zn star contains all those a bar belonging to Zn such that GCD of a with n is 1, means it contains precisely phi of n elements. Phi of n elements. Now we will state the Euler's theorem and its immediate corollary, which is nothing but Fermat's theorem. Okay. So what is the Euler's theorem without proof? Without proof. If GCD of M if GCD of M is 1, then or n is 1, then a raised to phi of n is congruent to 1 mod n. 1 mod n. Okay. And Fermat's theorem, if p is positive prime integer, if p is positive prime integer and a belongs to z is such that p doesn't divide a, then a raised to p minus 1 is congruent to 1 mod p. 1 mod p. Proof is too simple. So for prime integer p, greater than 1 and a belongs to z with p doesn't divide into a, GCD of a with p is equal to 1. GCD of a with p is equal to 1. Now, for positive prime integer p, phi of p is p minus 1. Since 1, 2, 3 dot dot up to p minus 1 are p relatively prime integers, p relatively positive prime integers to p less than p. Sorry, p minus 1. Okay. Phi of p is p minus 1. Therefore, by Euler's theorem, a raised to phi of p is congruent to 1 mod p, since GCD of AP is equal to 1. Therefore, a raised to p minus 1 is congruent to 1 mod p. A raised to p minus 1 is congruent to 1 mod p. So this is the simple proof of Fermat's theorem. Very useful theorem for finding the remainders. Corollary. If p is prime integer, if p is prime integer, then a raised to p is congruent to a raised to p is congruent to a mod p for any a belongs to z, for any a belongs to z. There is no any restriction here. For a prime integer p, a raised to p is always congruent to this. So proof. Case 1, if a belongs to z is such that p divides a, then p must divides a raised to p, and therefore p divides a raised to p minus a implies a raised to p is congruent to a mod p. Case 2, if a belongs to z is so that p doesn't divide c. If case 2, if a belongs to z is such that p doesn't divide a, then GCD of AP is 1. Therefore, by Fermat's theorem, a raised to p minus 1 is congruent to 1 mod p. Moreover, a is congruent to a mod p. Is it clear? Because p divides a minus a, which is 0, implies a raised to p minus 1 into a is congruent to 1 into a mod p. Therefore, a raised to p is congruent to a mod p. From case 1 and 2, result is proved. Use Fermat theorem to verify that. Use Fermat theorem to verify that 17 divides 11 raised to 104 plus 1 plus 1. So solution, Here 17 is prime number, 17 is prime number, and 11 belongs to Z is such that GCD of 11 with 17 is 1. Therefore, by Fermat's theorem, P is equal to this, A is equal to this. By Fermat's theorem, A raised to P minus 1 is congruent to 1 mod P. Implies 11 raised to 17 minus 1 is congruent to 1 mod 17. Therefore, 11 raised to 16 is congruent to 1 mod 17, 1. Applying division algorithm to 104 and 16. Now, 104 is equal to 16 into. If I divide this by 16, 96, 16 6 are 96 plus 8. 104 is equal to 16 into 6 plus 8. Is it clear? So, by 1, 11 raised to 16 raised to 6 is equal to 11 raised to 96 is congruent to 1 raised to 6 is equal to 1 mod 72. We are getting this. We are getting now that 8. This remains. Okay. So for that we find 11 square. 11 square. Is it clear? We have 8 power. Okay. Now 11 square is equal to 121. If I divide it by 17, okay, is congruent to 121 by 17. Okay. So 17, 7. 119. Okay. So what is the remainder? That is 2. Modulo 17. Since 17 divides 11 square minus 2. Is it clear? 11 square is 121. 11 square is 121. 121 minus 2 is 119 is divided by 17. So 11 square is congruent to this. Therefore 11 raised to, if I take its power to be 4, okay. So 11 raised to 2, its power is 4 is equal to 2 raised to 4 modulo 17. 11 raised to 8 is congruent to 16 modulo 17. 16 modulo 17. Is it clear? This is your 3. So from 2 and 3, from 2 and 3, 11 raised to 96 into 11 raised to 8 is congruent to 1 into 16 modulo 17. Okay. But what is this? 11 raised to 104 is congruent to 1 mod 16 mod 17. Is it clear? Now 1 is congruent to, now 1 is congruent to 1 mod 17. 1 is congruent to 1 mod 17, which implies is 11 raised to 104 plus 1 is congruent to 16 plus 1 is equal to 17 is congruent to 0 mod 17. And therefore 11 raised to 104 plus 1 is congruent to 0 mod 17. Now if A is congruent to B mod n, then A and B leave same remainder when divided by 17. Okay. Or this implies 17 divides 11 raised to 104 plus 1, okay, minus 0 is equal to 11 raised to 104 plus 1. Okay. Thus, by Fermat's theorem, thus 17 divides 11 raised to 104 plus 1 plus 1. Is it clear? Next example. Find the remainder when 2 raised to 105 is divided by 11. Find the remainder when 2 raised to 105 is divided by 11. So here 11 is prime integer and 2 belongs to Z is such that 11 doesn't divide 2. That is GCD of 2 and 11 is 1. Therefore, by Fermat's theorem, by Fermat's theorem, 2 raised to 11 minus 1 is congruent to 1 mod 11. That is 2 raised to 10 is congruent to 1 mod 11. Right. This is 1. Now here find the remainder, find to 105. Now 105 will divide by 10. 10 into 10 plus 5. Okay. Therefore, 2 raised to 10 to the power 10 is equal to 200. 2 raised to 100 is congruent to 1 raised to 10, which is equal to 1 mod 11. This is 2. Okay. Now we have to find out 2 raised to 5. Now 2 raised to 5 is equal to 32. It's congruent to, if I divide 11, is 10 mod 11. Is 10 mod 11. Is it clear? Therefore, this is 3. From 2 and 3, 2 and 3, 2 raised to 100 into 2 raised to 5 is congruent to 1 into 10 modulo 11, and therefore 2 raised to 105 is congruent to 10 modulo 5, 10 modulo 11. Okay. And 10 leaves the remainder 10 when divided by 11. When divided by 11 implies 2 raised to 105 leaves the remainder 10 when divided by 11. When divided by 11. Is it clear? Find the unit digit of 9 raised to 102. Find unit digit of 9 raised to 102. So if I divide it by 10, what will be remainder? If I divide, say, any number by 10, what is the remainder? That remainder is always unit digit of it. If I divide 1, 2, 3, 4 by 10, this 4 is the unit digit. So, for this, we will divide. For this, we divide 9 raised to 102 by 10 and find remainder. Remainder, which is unit digit of 9 raised to 102. Okay. So here 5 of 10. What is the 5 of 10? Here that m doesn't divides 10, doesn't divides 9, and 5 of 10 is equal to. So 3, then 7, 3, 7, 9. Since, 4. 1, then 3, 7, 9 are 4 positive integers. 4 positive integers less than 10 are relatively prime to 10. By Euler's theorem, 9 raised to 5 of 10 is congruent to 1 mod 10. Is it right? So Euler's theorem states that a raised to 5 of m is congruent to 1 mod m if GCD of m is 1. GCD of m here, GCD of 9 and 10 is 1 and 5 of 10 is 4. Okay. So Euler's theorem this. So 9 raised to 4 is congruent to 1 mod 10. 1 mod 10. Even if I take 9 square is 81. 81 is congruent to 1 mod 10. I can also take that one. It is not necessary to apply here Euler's theorem also. Not necessary to apply Euler's theorem. Now 102, this is 1. Is equal to, I will divide it by 4 into okay plus 2 okay from 1 9 raised to 4 raised to 25 is equal to 9 raised to 100 is congruent to 1 raised to 25 is equal to 1 mod 10. This is 2. Okay. Now 9 square is equal to 81 is congruent to 1 mod 10. Because 10 divides 81 minus 1 from 2 and 3 from 2 and 3 9 raised to 100 into 9 square I want 102 okay is congruent to 1 into 1 modulo 10 and therefore 9 raised to 102 is congruent to 1 mod 10 and 1 leaves the remainder 1 10 divided by 10 and therefore 9 raised to 102 leaves the remainder 1 10 divided by 10 therefore unit digit of 9 raised to 102 is 1 is it clear? So these are very good applications of Fermat's theorems and Euler's theorem, and obviously Fermat's theorems and Euler's theorems are applications of congruence modulo n relation defined on set of integers. So congruence relation plays a very important role in study of integers, and which is the basic of number theory course. If you are going to study higher mathematics, you will come across the number theory course at TYBS mathematics or at MSc level, and these congruence relations plays a very important role in that course. So with this discussion, we will stop this lecture here. Thanks for listening lecture carefully, and in fact with this lecture our third chapter, primes and theory of congruence, is over here. Go through each and every example. If you have any difficulty, you can ask personally to me, but attend or listen each and every lecture very carefully to understand congruence relation, Fermat's theorems, Euler's theorem, because they are very important as we have studied their applications. Thanks again. Bye bye.